Okay, thank you. I am Bob Peterman. I'm a faculty member at Kansas State University, and I'm going to be giving this talk with Steve Mattson, who's Director of Concrete Technology at Nortrak. And we're going to be talking about using available technologies to select the pre-stressing wire indent characteristics to meet the unique requirements of pre-tensioned concrete railroad ties. And as we get started, I just wanted to acknowledge several people. First of all, thank the FRA who funded all of the work that I'm going to be talking about that was conducted at Kansas State University. And also my colleague, Terry Beck, who's in the Mechanical and Nuclear Engineering Department at K-State. Terry and I have been working together on this and related topics for the past 18 years. And also the work I'm going to be presenting was conducted by many graduate and undergraduate students over the past 10 years. In fact, I wanted to clarify something right off the bat. If you hear me say that we did something, it could mean that there were students working into the wee hours of the morning actually getting it done. Okay, so today, the overview of the talk, I'm going to talk about the background of the work that we've conducted, then talk about systems tests that are available to evaluate the concrete tie system, quality control tests, and then a new wire indent property that I'm calling the bite per length. And then Steve Mattson is going to go through a recent case study. And then finally, I'll wrap it up talking about some additional ongoing research. Okay, so when an indented pre-stressing wire is made, after the wire is drawn down to its final diameter, it goes through a series of 3 indent rollers that actually produce the indentations. And this is kind of a picture of the indent roller on one of the indent rollers on the left-hand side, and on the right-hand side is the indents in the wire that are a result. Okay, and because these indents are rolled in, there's really a unique opportunity with indented wires. And that is the bond of indented pre-stressing wires can be controlled by the type, depth, and spacing of the indentations that are rolled into the wire. Therefore, these wire parameters can be optimized to meet specific needs. Okay, and so has been considerable FRA-funded research conducted during the past 10 years to evaluate the bond and splitting characteristics of indented wires used in the manufacture of pre-tensioned concrete ties in North America. This work has resulted in new assessment methods and qualification tests for both the pre-stressing wires and the overall system. So the primary wire requirements we have for a railroad tie are it needs to provide enough bond to the concrete so that the design pre-stress force will be available at the rail seat location and not result in longitudinal splitting with the corresponding concrete mixture and reinforcement edge distance. And so the fact that we're trying to provide enough bond at the rail seat really leads us to the rail seat positive moment test, where we verify that when we load the member at the distance of the rail seat from the end, that we will indeed have the proper pre-stress force prior to cracking. And so if I focus in on that end region, then as we talk about the length it takes to transfer the pre-stress, that's the transfer length, a lot of times people will consider that transfer length to be a single value, that if I'm using a certain wire and a certain concrete strength, that gives me a certain transfer length. And I think that's flawed thinking, and we really need to stop thinking about a transfer length that way. Rather, a transfer length is really, since we're producing many ties each day on a bed and many days of production, we really need to think of our transfer length as a distribution, where there'd be a mean as well as a standard deviation. And so if we're just doing the Arima check for first cracking into the rail seat, a transfer length that looked like this right here, or one that I'm showing a distribution to the right, or one to the left, they would look the same under the Arima test for first cracking. And so the one on the right would be prone to occasional failures or not have as much reserve capacity after first crack. The profile I'm showing over here on the left is very short and could result in splitting issues. So I think the ideal transfer length is somewhere in between, and I like to think of that maybe the 9 to 15 inch range for a tie that has a rail seat around 21 inches. That's going to allow for some variability and still give allow reserve capacity. Okay, so the quality assurance tests that are available to verify the overall system are automated transfer length measurements and the newly adopted Arima splitting resist test, SRT, that's now in Chapter 30, Section 4.2.4.1. Okay, in terms of automated transfer length measurements. Well, this is a picture of the automated system that we developed at Kansas State University. And this we can set on the top of a tie before and after detensioning. And we'll place that there, and this automatically goes across the tie. Okay, so that instrument, it traverses across the tie. We do that before and after detensioning. What that does is it takes pairs of images of the surface of the concrete. And by doing that before and afterwards, we do digital image correlation and determine the strain profile at the end of the member. This is a picture of a strain profile that comes directly out of the automated transfer length measurement. And it with a little bit of crunching time, about 10 or 15 seconds, it'll plot and what the transfer length was for that specific end region. And what we're looking for is the point where the surface strain comes up to an approximate plateau. Now, this plateau is not uniform because the tie cross-section changes, so we have a way to calculate that, determine that based on shape factor. So that's automated transfer length measurements. The second way we have to evaluate the overall system is through the Arima splitting resistance test. And in this test, we take our current tie geometry, and from that we can produce either a prism or an actual tie section where the ends of that member are reduced, have a reduced cover, and the reduction is about 25%. So we reduce the edge distance by about 25, and if we make 6 of these, we have 6 ends without splitting, then we know that our tie, the actual design, has a robustness against splitting. And so that's a way to look at the overall robustness of a given design. Okay, so the quality control tests that can be used to assure the bond quality of pre-stressing wires include ASTM A1096 pull-out tests, and that test method was adopted in 2015, and also automated non-contact wire indent scanning of the wire. We have a wire indent scanner, and we can put the wire in a device that allows us to accurately measure the indents. So the ASTM A1096 pullout test, again, this is a standard pullout test that was adopted by ASTM in 2015. And in that pullout test, we take a indented or smooth wire and we cast that inside a steel can with a 4-inch diameter and then fill that with mortar. And when the mortar is between 4,500 and 5,000 psi, then we pull the bottom of the wire at a rate of 2,000 pounds per minute while we monitor the end slip at the top free end. And the ASTM pullout test, the value is the pullout force value when the top slip, the maximum force before the top end slip reaches 1/10 of an inch. Okay, and this is a picture of a pullout test being conducted. So the can here, it contains this is a large indented wire. This is in a mortar. It rests on this top support and it's being pulled out at the bottom while we measure the top end slip with an LVDT. So at Kansas State University, we looked at 13 different indented wires that were used in the manufacture of pre-stressed concrete ties around the world. And we did this pullout test. We're on these 13 different wires, and the curves here are the pullout force versus end slip. And these are the average curves for 13 different wires, or the average curves for 6 different individual pullout specimens for each of the 13 wires. And so again, the ASTM A1096 value is the maximum point on the curve before we get to an end slip of 1/10 of an inch. And when we took that data, we saw that those pullout values correlated extremely well with transfer length. And so in this case, the measured transfer length, we developed an equation that had an R squared, a coefficient of determination of 0.954. And that held true for various release strengths at 3,500, 4,500, and 6,000 PSI. The equation that we developed for 5.32 millimeter wires was essentially the transfer length equal to a constant minus a function of the release strength, and then minus another factor that depends on the A1096 pullout value and the initial release strength. Okay. The second way we have to evaluate the wires is through automated non-contact indent scanning. And this is a picture of an indent scanner that we developed at Kansas State University. It uses a CNC lathe where we put the wire in the lathe, and then we have a line laser that we measure the distance to the surface of the wire. And I'll show this in operation. The wire over on the right-hand side is rotating. And these are physical measurements we have of the wire and the indents. Okay, and you can see this is a heat map is being generated as we gather the data. These are actually measurements. So the laser that I'm showing on the right, there's 800 points along that laser, that purple line that's showing, and we measure at 720 points around the wire during each revolution. So we then can extract all types of parameters for the wire indents, and we showed that the transfer length had a strong correlation with the indent volume, sidewall area, and release strength. And again, R squared was 0.88, which is excellent correlation. This is a typical indent report that we have after scanning a wire. We have several things. So this is a picture of the particular indent, and I've kind of hidden the wire identification, but it's a wire we scanned this spring. And these are the average indent profile, which would be in this north-south direction, which is the line I'm showing here in the diagonal. This is the average profile for each of the 3 indent rows. Typically, an indented wire has 3 rows of indents. Often 2 are in the same orientation and 1 would be in the opposite orientation. But from the indent scanner, we automatically get for each row the depth, length, angles, sidewall lengths, basin length, volume, and this new quantity that I'm calling byte per length that I'm going to discuss in detail. But this comes from the indent scanner, and the nice thing is these indent parameters are excellent predictors of both bond and potential splitting. So to understand this a little bit better, I want to go back and refer to the original prisms tests that were conducted at Kansas State University. And if you're been to any of the former rail tie conferences, you would have seen this work. But we manufactured concrete prisms using 4 wires. The prisms were 3.5 inch by 3.5 inch cross section. And we used, in the original study, we used 13 different reinforced pre-stressing wires, all 5.32 millimeter. And you can see these all had various indent types and shapes. We manufactured 3 prisms in a row, and we made sure that we cured the concrete cylinders we cured those to the same temperature as the prisms, so we knew the exact release strength. When we cast the prisms, we cast brass inserts into the sides so we could measure baseline points and take measurements again after detensioning to determine the transfer length. Now, at the time of the prisms, the automated transfer length device was not available, but also we wanted to make sure we get long-term transfer lengths over a year period. And so we didn't want to rely on digital image correlation for long-term measurements. So this is a typical plot of the surface strain that we got from the prisms. And from there, we could determine the break point where the transfer length would be for this particular case. Okay, so this graph shows the average transfer length values are the diamonds and the range of transfer length for all 6 ends for each wire type. So these are the 13 different wire types. So we labeled those generically from WA through WL based on when we received them. And you can see there's a range of values that we saw for the transfer length and average value. And the two wires I want to focus on specifically are this wire WA, which was the smooth wire, did not contain any indents, and WJ, which was chevron shape indented wire. So the smooth wire had an average transfer length of 15.2 inches. And since the transfer length, I showed that graph of surface strain is approximately linear, we know that it's an average bond per length is reasonable assumption, and that bond per length will be 7,000 pounds, the total force on each wire, divided by the transfer length of 15.2 inches, or 460 pounds per inch. That was the bond that was achieved during that transfer length measurement. So that bond is due primarily to the Hoyer effect. The Hoyer effect means as we stretch the wire, the diameter is reduced due to Poisson's ratio. When we then release that pre-stress force back into the concrete, the wire wants to expand to its original diameter and puts a normal force onto the concrete. And so we're really developing this bond through friction. So now if we look at the wire WJ, the average transfer, this is the chevron indented wire, that had an average transfer length of 9 inches. Now, the amount of that bond that could be apportioned to the Hoyer effect would be the 460 pounds per inch that we got for the smooth wire times the 9-inch transfer length, or about 4,140 pounds. Therefore, the remaining force, the 7,000 minus 4,140, or 2,860 pounds, we could attribute to the indents. Okay, because of those indents, we were able to reduce the transfer length from 15.2 down to 9 inches due to the indents. So if the indents are responsible for 2,860 pounds, we measured the pitch of those indents at 0.221 inches, meaning there's 54.3 indents per foot along each row of that wire for WJ. So our force per indent then would be the force attributed to the indents, 2,860 pounds over the 9-inch transfer length. And if we put that into convert to feet and divide that by the total number of indents, there's 54.3 in each of 3 rows. We come up with a force of 23.4 pounds per indent that on average that's being transferred. Okay, so I asked, what's the perpendicular bearing stress at the indent edge? Well, those indents, after scanning, we measured had an average depth of 0.0048 inches and an average width of 0.163 inches. So I can calculate the average bond stress as just the force divided by the perpendicular projected area, which is 23.4 pounds divided by 0.163 and 0.0048, or 29,920 PSI, which is much, much greater than the concrete strength. We detentioned these at 4,500 PSI. Simply means the concrete crushes. So as we detention, the concrete is being crushed at those indent bearing surfaces, and it can't go inward to the wire. Therefore, that crushed material has to be displaced. A little bit may go into the concrete voids, or the air voids, but most of it is being displaced and it has to go outward. And I believe that's what's really causing the reduction in transfer length, is we're pushing this concrete outward and we get more and more normal forces and contributing to the transfer. And this is kind of analogous to a snowplow. If you see the snowplow, it has to displace the snow as it goes along. And as that wire is slipping at the end of the concrete, and we measure end slips during the detentioning process, that material has to go somewhere and it's being plowed. And if we have a small plow, it's not so much of a deal, but a larger plow, we're plowing a lot more material, and that can have some serious effects. And so I ask, what can be done? Well, if I'm looking at this snowplow effect, this has a rectangular shape. So this is going to can plow a certain amount of material. If you think about this as the bearing surface of an indent, there's a certain amount of material that's going to be displaced. That area is going to be the width, in this case, the snowplow or the indent, times the height or the depth of the indent. Well, if we have an indent that would feather out toward the end, we'd have a lot less plowing area. In this case, it's only half the base times the height. And so as we look at possible indent shapes, the Europeans have actually broken these down into specific styles. The T2 style would be an indent that would be deep all the way, uniformly deep all across the indent width. And by width, this will be the north-south direction. This would be east-west. This distance from here to here would be the indent length. But the T2 style is deep all the way from the north to south, and you see a crisp edge on both the north and south direction. The T4 style indent is deep in the middle, but then tapers out to 0 on this north and south edge. Okay, so the new quantity that I'm talking about based on our work at Kansas State University is what I'm calling byte per length. Byte per length is equal to the average indent width times the average indent depth divided by the average pitch. And it's a way to quantify the amount of concrete that is displaced as the wire slips through the concrete during detensioning. The normal range of byte per length is between 1 and 10 for most reinforcements, and byte per length really represents an area per unit length of that indent. And so for those same two indent shapes, what I'm calling the byte is shaded green here. So it would be this shaded area then divided by the pitch or the distance between indents as we run in and out of the page. And so at this point, I'm going to turn this over to Steve Mattson, who's going to talk about a recent a case study that he's been involved in at Nortrak.
Thanks, Bob. And thanks UIUC for the opportunity to present at this year's Tie and Fastening Conference. I've been in the concrete tie manufacturing industry for over 24 years now, and this research that Bob and his team have been conducting has been extremely helpful, and I'm excited about the tools that are now available for the concrete tie designer to be able to choose and use a larger diameter wire that can create a product that is free from end splits. And so it's pretty exciting. So the case study I'd like to talk about, we've got a product that's been designed to be interspersed amongst wood ties. That's a very small tie compared to conventional concrete ties. And because of that, we needed a larger diameter wire. We developed this about 2 years ago, and we used our sister company in Austria, the voestalpine wire drawing plant in Austria has a 7.5 millimeter wire that we used to qualify the product, and we went through all the qualification testing and checked for any potential for end splitting. It worked very well for us for the initial qualification of the product. Did the Arima 3 million cycle repeated load tests and all that work. This is a profile of what that wire looks like. Again, it's a 7.5 millimeter diameter. The profile from north to south across the indent is like you see here. So it shows a T4 style indent with it feathering out at the north-south edges, going up to a little over 4 thou deep. We're in need of a local domestic supplier to be able to meet Buy America requirements. So that's why we started this project and went to qualify that supplier, which is Nucor LMP. And we started with an off-the-shelf product that they had available. The profile for that wire is, as you see here in blue, and it's very similar to the product we had proven. So we thought that was a good starting point. We ran the Arima split resistance test. This is the tie with the reduced cover, as Bob explained, and that's all around the bottom edge, top edge, both sides, and extends, a distance in from the end of the tie. And then you monitor these ties or very large prisms for any potential cracks. Well, the off-the-shelf product didn't perform so well. So we ended up getting cracks, despite that the indent profile north to south looked very similar. Now, this work was done in advance of the work Bob did on byte per length. So we went back then and looked at what are the key differences between these two wires. The proven 7.5 millimeter wire had a pitch of 0.328, whereas the Nucor off-the-shelf product had a pitch of 0.224. So many more indents per foot of wire with the Nucor at 53.6 versus the Austrian wire at 36.6. So we decided, hey, let's analyze that with the wire, the non-contact wire scans, and see what the byte per length is. The proven wire ended up with a byte per length of 4.1. And lo and behold, the off-the-shelf product had almost double at 7.9. And that was really the aha moment for all of us. And we said, well, let's use the byte per length as a way to pick a wire that is going to perform much better. So we went back to Nucor, and they graciously came up with some indent rollers that mimicked the T4 style versus the T2 style, and with a much shallower depth. So the goal there was, let's get the indents fewer per foot, more in line with the T4 standard. Let's go with a very shallow depth to protect against end splits. And let's make sure that you have that fade going from north to south. So what we ended up with was a wire that was a T4 002 or 2 thou depth with that triangular style indent. And this is what that plot looks like. So, you know, on the surface, you look at this and you say, you know, you'd think that the blue wire or the off-the-shelf 8mm product that was offered would have been a great match compared to our proven European supply. But when you look at byte per length, it's almost double, even though the profile matches. So using byte per length, we said, you know, let's get an even lower byte per length, see how that performs. As long as we have bond, that would give us the best protection against end splits. So we went ahead and made some ties. And here's a photograph of our bond test machine at our lab. And this is the product in that test. You can see that there's a constant moment region at the rail seat where we apply load. And then there's a support at roughly 28 inches on center on the bottom. And then we apply dial gauges at the end of the tie with contact at the lowest tendons in the tie looking for bond loss. We monitor that for bond loss. So we took the tie up to the first crack load test. You hold that for 3 minutes, passed without any problem. The Arima test procedure is to then increase the load up to 1.5 times the no crack load and monitor for any bond loss for 3 minutes. Well, we did that, and right near the end of the 3 minutes, we consistently got bond loss before we hit the 3-minute period. So we were close, but not good enough. So we went back to Nucor and said, let's increase the depth ever so slightly. So look, going from the 2 thou depth up to 3 thou depth. Again, the same north to south fade, or the triangular plow, if you will, like Bob talked about, and the fewer indents per foot. This wire plotted showing compared to all the other types is the red one in the plot, and we ended up with a byte per length of 2.7. And since the indent style and pitch are the same as the 1.9 byte per length that we tested, you could really look at this difference in area on this profile as an increased byte per length. Now you can't compare that to the T2 style because the T2 style pitch is much different. But it's a pretty good indicator for comparing same indent styles. And here's photographs showing all 4 different wires that we tested, starting with the proven Austrian wire from our sister company that works very well, to the off-the-shelf product that Nucor had that was pre-existing, not necessarily for wire ties, it's for other products that they had that, and now the new and improved Nucor 8.8mm wire that's excellent for railway ties, and the 2 progressions we did. So we went back to the Arima RS positive bend test, hold it for 3 minutes, pass without a problem. The RS positive bend test, 3-minute hold, that also passed. We went and continued loading that tie to see when bond loss would occur, and bond loss ended up occurring at over 300% the design no crack load. Now the typical bond test load is 150% or 1.5 times the no crack load. And we doubled that before we saw any bond loss. So we see that as an excellent test result. And then we went on and continued to load the tie to failure, and failure occurred at over 350% of the design no crack load. The failure mode was bond loss of the tendon, which then led to a compressive failure at the top of the rail seat, which then progressed to shear cracks, as you'd expect. You can see here, this photograph shows the end of tie wire pull-in and or bond loss of that product. I see this as the preferred failure mode. And again, that's at 3.5 times the design no cracking load. And that's a load that you should never see in track. So it's really an extreme test for making sure that the product's going to behave with an acceptable failure mode. And for me, you know, no cracks is an acceptable failure mode. And then lastly, the Arima split resistance test, which is also passing. We also conducted an Arima 3 million cycle repeated load test on this product, which also passed. So in summary, for any given wire edge distance, wire jacking load, and concrete release strength, I encourage you to consider the following items when qualifying a new wire source. And it's important to recognize these things because your design may be different with a different edge distance and a different jacking load and really diameter of wire. And you may have a different release strength. But for those particular parameters, if you pay attention to using wire scans to determine a byte per length number, it's an excellent tool to help dial in your process to get a wire that will give you the necessary pre-stress force in your product without potential for splitting. And then the scans themselves are an ongoing excellent quality assurance tool for the wire supplier to ensure consistent quality of their product. So, you know, whether they do that online for every single coil or whether they do that weekly, it's an excellent tool to make sure that the indent properties haven't changed or aren't changing as the indent roller wears and as the indent roller pressure is changed. Second item I recommend is to conduct Arima rail seat positive bending tests for no crack load, 1.5 times no crack bond load, and then carry those all the way up to ultimate and make sure that the failure mode at ultimate is free of end splits. Third item would be to conduct the Arima split resistance test to ensure adequate reserve capacity against end splitting. The way I see the Arima split resistance test is it can really help you find if you've got a design that's really close to the edge. It passes all the other tests, but might be just borderline to causing cracks. The split resistance test is going to find those. It's got the method with the reduced cover helps bring any of those that are you know near that tipping point to the surface and helps you make sure you've got enough reserve capacity against end splitting. Fourth item is to do the ASTM A1096 pullout test, as Bob mentioned, and that's really to establish a baseline. Once you've done all the above and you've proven you've got a wire that works, make sure you get an ASTM 1096 pullout test so that you have a baseline for your particular supplier, and then repeat that annually to monitor for any drawing lubricant related wire adhesion changes. So that Hoyer effect piece of the puzzle that Bob's talking about versus the indent piece. The scans catch any changes to the indent, but the ASTM A1096 test is going to catch any changes to the adhesion, which is affected by the drawing lubricant used when pulling the wire. And that's all I have. Thanks, Bob.
Great, thank you, Steve. Go back here and kind of wrap this up here. So I'm going to talk I think, can you confirm you can see the screen, right, Steve?
I can.
Okay. I'll talk about some additional work that's being conducted. We're currently conducting additional work under an FRA contract to establish correlation of the two existing wire assessment methods, both the ASTM A1096 pullout tests and non-contact indent feature extraction, with resulting transfer length values for larger diameter pre-stressing wires. And so the industry partners that we have, we're working with Nortrak, with Steve Mattson's company, also Nucor LMP is supplying the wire, and also Rail One, who also manufactures ties with larger diameter wires. And the main reason for doing this is we had excellent correlation with 5.32 millimeter wires with both indent scans and ASTM A1096 values. Our goal is to take that work and extend it to larger diameter wires so that we can hopefully develop correlation equations that will be valid for all wire sizes. For example, once we establish this correlation, if you wanted to make a tie maybe with a 7 millimeter wire or a 9 millimeter wire, you would have the tools and the guidance of how to do that. What the indent scan, from an indent scan, you'd be able to determine or have a very good estimation of the transfer length that you would get with that, with the given release strength. And so in the current study, we're looking at both 8 millimeter wires and 10.5 millimeter wires. The 8 millimeter wires, we're using a smooth wire, two of the T4 indent depths, which have that kind of that triangular shape, deep in the middle and shallow out to the end. We're using a depth of 0.002 and 0.005, kind of the two, I guess, what might be extremes, because you could go deeper. Then we're also using the T2 style indent that has a closer spacing. That has a depth of 0.004. For the 10.5 millimeter wires, we're using a smooth wire and a T4 style indent that feathers out to the edge with a depth of 0.004 and 0.008, and also a T2 style with a depth of 0.004 and 0.008. And we're looking at release strengths of 4,500 PSI and 7,000 PSI. I also wanted to note that as we talk about the T4 style indent, as that feathers out in the north to south direction, there's a very practical aspect to that from a wire production standpoint. A wire producer, such as Nucor, there'll be some tolerance in the wire depth that they can't produce a wire at exactly 3,000 depth or 4,000 depth. There's going to be a plus or minus. And if you go with a T4 style indent, that plus or minus is going to have a lot less of an effect on the bite per length than a T2 style indent, just because the T2 style indent has that full depth all the way across in the north-south direction. So think of the T2 as the rectangular areas base times height. The T4 is more of a triangle, 1/2 base times height. So on a T4 style indent, you can accommodate more variation in depth without affecting the bite per length as much. So this is a photo showing the four 8 millimeter wires that we're using in the study. There's a smooth wire. You can see the T4 style indents. The top one is a depth of 0.02, bottom one depth of 0.05, and then this T2 style indent. You see the full indent is defined, both the north and south direction, and you can see this has a tighter pitch. So we'll be able to look at bite per length in the correlation expressions with transfer length, and hopefully that'll apply as it did with Nortrak's experience with splitting. We'll be able to give guidance as that as well. So from preliminary results from the new study, ASTM A1096 pullout test with the 4 8 millimeter wires, and you can see the smooth wire is the bottom one here, and this is the pullout force on the vertical axis versus the wire free end slip, the top end slip. And so a smooth wire, the bite per length is 0. There is no bite. And what happens with a smooth wire, as soon as we initiate slip, the bond goes down. And this is kind of think about the reverse Hoyer effect. When we initiate slip or pull through, that wire is reducing in diameter. And since there are no indents, the bond will actually drop as soon as we initiate slip all the way through the pullout specimen. The same thing we found holds true for a pretensioned member. In the original K-State study, we did transfer length tests as well as load tests with smooth wire. And on a load test, you can get a reasonable transfer length, and we showed that earlier. For the smooth wire, we had a transfer length of 15.2 inches. However, when we loaded that wire, as soon as you get a first crack in a flexural test specimen, when that crack opens and we try to demand more tension, we get immediate failure. So smooth wires are not good for flexural applications if there's a chance of crack, because they essentially provide zero reserve capacity beyond cracking. As we go up in the pullout test, we see the T4002 had a bite per length of 1.9. Here's the T4005 had a bite per length of 5.5. And up here, the T2 with a depth of 0.04 had a bite per length of 7.9. That's because of the closer pitch of 0.22 inches. So we see the pullout values are going up nicely with the increased bite per length. And so we really expect this to have a strong correlation with the transfer length. I'm looking forward to getting the results from both the 8mm and the 10.5mm wires and correlating bite per length back to transfer length. So in conclusion, the two evaluation systems, evaluation tests, both transfer length measurements and the newly adopted Arima splitting resistance test, can be reliably used along with the two-wire bond evaluation methods to successfully develop new tie designs with any wire diameter. Bite per length is a very useful wire indent parameter that can be rapidly determined from the non-contact wire scans. Once we scan the wire, and I showed how quickly that goes, the reduction of that data is automated through software, and we can determine bite per length very rapidly, matter of seconds after scanning a wire. And current work is in progress that we're expecting to result in correlation expressions that can be used for the initial selection of wire parameters for future designs. So with the current work, we will tie that into the K-State work where we did 5.32mm wires along with 8mm and 10.5mm. We expect to develop correlation expressions that'll be valid not just for those three sizes, but for all the in-between sizes as well. And with that, I wish we were in person. I would ask for questions, but that will conclude the talk, unless, Steve, did you pick up on anything I missed?
No, I just wanted to, I guess, reinforce that, I've been in this industry for 24 years, and I remember making a request to the Prestressed Concrete Institute 24 years ago that it'd be nice to see more technical data on how to choose and select indented wire. And it's been long in coming, but I think we have the tools now that help you do that. That's the bite per length is an excellent technical parameter about the indent that can help you design ties that are crack free as far as any potential for end splitting. So we're very, very excited about this work and appreciate all the work that you and your team have done, Bob. Thanks.
Thanks, Steve. And I will stop the recording.